As I mentioned earlier, so now we'll be focusing mainly which the topic is for that the measurement of output. So as I mentioned earlier that the most common way of evaluating the output as you calculate either the open circuit voltage or you calculate the short circuit current and also power, and this both as a function of time. Okay, this both you calculate as a function of time. So basically what you see, like you have your, if in this case you plot VOC, it will be like this kind of curve you will see, and in the x-axis you have time. Okay, and a similar kind of graph you will see if you are plotting the short circuit current here. So both need to be plotted against, okay, this axis also you have time. Okay, so this is the, for a different bending cycles you calculate the output in terms of open circuit voltage and short circuit current. Okay, now many this nano generators basically device have been judged solely on the equivalent peak of the open circuit voltage values, but this sometimes could be misleading, as I said. And also for a useful implementation of the harvested energy, the device, it's quite simple that cannot operate at open circuit, but there has to be a load which must be connected. Okay, so if I just fairly draw the how this device will look like, so let me just draw it here. So how you are going to, so suppose you have, this is the device which is under measurement. Okay, and this you are measuring like this, and here let me just draw the rectifier circuit. So you have some rectifier circuit which is made from the diodes. Okay, so this is the rectifier circuit you need to prepare from the electronics. Okay, and this has to be connected to rectify the, so this is the rectifier circuit which you are going to use, and your output of the, so this is the device under measurement, it is called device under test, DUT, or material under. So this is the output which will go here, okay, which will go here. Let me just, yes, sometimes it becomes very confusing thing for me. Let me remove this. It should be, let me see, it should be connected to, I think this is going to, this should connect to this terminal, and this should go to the opposite, that is positive, and this should go to here, okay, and from here you are actually taking the output, okay, and here you have a capacitor, okay, and then you have a capacitor over here, and then you have a load resistance. So this is a capacitor and this is what is your load resistance, which will be connected, and then finally you are measuring this, okay, this two terminal will be measuring the whatever your voltage, okay, this will measure, here you will measure the voltage, that therefore this will go to where, this terminal, this two terminal will go to your DSO, that will go to your DSO, okay, this two terminal will go to DSO. Now as I said that for the useful implementation of the harvested energy, the device cannot operate in the open circuit, because open circuit, what does it mean? You know that open circuit open circuit mean your load resistance is infinity, so that cannot be an infinite value actually, okay, because that has to be some of the some value, some has to be connected, some load has to be connected, okay, although there are a number of complex circuit that is have been developed. This is the basic circuit, you know, this is the very basic circuit for energy harvesting. This is very uh, basic circuit for energy harvesting, but there are so many other development has been done to optimize the power transfer. But the most basic test that is common for all the other energy harvesting technologies is to measure the voltage generated when the harvester is connected directly to a range of resistive load. So basically you are going to measure this value of voltage for a range of RL. So you will actually vary rho, you will actually vary it for a range of RL. You are going to measure V, okay, for a different, and this was performed for uh, the devices, uh, and then the voltage is recorded, okay, for a different values of. So let's say you are going to vary this value of load resistance, because now see your what is your maximum power transfer theorem says that the input impedance is, if input impedance is equals to the output impedance or load resistance, then only you will get maximum power. This is very fundamental thing. So whatever the internal resistance which is offered by your device, if that matches with the load resistance, then only you will get maximum power. Okay, so the power which you are going to calculate from the voltage which you are measuring, that can be written as P equals to V square by RL. Okay, so if you are wrenching, let's say you are wrenching your, and you know that the material you are using a piezoelectric machine, it has a very high resistance. So maybe if you are taking the value of RL, let's say you are varying RL from, let's say, 1 mega ohm to, let's say, some 100 or 100 mega ohm. Okay, let's say you are measuring this is for 100 mega ohm, and for each and every value of this RL you are calculating this instantaneous power. So this power is for a particular, so you just can write down it is as P power as a function of RL for a particular value of RL, that you can write down as V, whatever the out velocity voltage you are getting at the circuit, by RL. That is how you can calculate this. Okay, and V, what is, you can say that this is the peak voltage which you are getting across the load resistance. So V is the peak voltage across RL. Okay, this is the peak voltage across the RL. It should be noted here that this expression is only approximate due to the effect of stray reactance in the load and measuring circuit. Okay, in general, the nanostructured piezoelectric energy harvesters, which we termed as nano generator earlier, the it has an active area. I mean, so if you have remember that uh, you have seen that we have a device like this. This is the film which you have deposited for composite film. So this is what is your uh, composite film. This is what is your composite film, And here you have an active area. What does it mean? Active area means you have deposited the area, not the complete area, but whatever the area you have covered with the deposition, that is what is your active area. Okay, so this is the part which you have deposited by an electrode. So this part you have electroded by, let's say, aluminium, or let's say you have deposited with gold or maybe copper or whatever. So this is the one this is what the one surface look like, and maybe the other surface. Now if you see the cross section of it, let me just show you the cross section of it. It may look like this. So this may be your device, and this is the piezoelectric material, this is the piezo material. So this is the piezo material. Okay, and let's say this is what is your electrode, top electrode, right? This is what is your top electrode. I am just reverting it, and maybe the bottom surface you have completely electroded. Okay, you have completely electroded by this, but still in this case the active area will be the area of this. So this will be the active area. Active area means this part, the part which I am going to now show in green color, that part will not contribute anything. So this part, okay, sorry, this all this part where you have not electroded, that part will not be contributing any charge generation. Okay, so only this part will be called as active area, and you can, if you see the cross section, it will be look like that. So this is the top electrode which you can see here, and this is the bottom electrode. This is what you call top electrode, and this is what is your bottom electrode. Okay, so when you are calculating this power here, when you are calculating this power, this, instead of this reporting this power, you are going to talk about power density. Okay, and then this, whatever the from the previous circuit you have seen, from that power will be calculated, that will be divided by this active area, that will be divided by this active area to get the power density. Fine. Okay, so that is you call as power density. Or sometimes you can also consider the volume of this. So if you just want to add the thickness, so let's say you have the thickness here as T, then your active area, let's say your active area has uh, A into B is what is your active area. Okay, and that could be multiplied by T to get the volume. So in this case, the device volume is considered as the active area multiplied by the thickness, and power density, that can also be. So your power density could have the unit of watt per meter cube or watt per meter square. Okay, these two uh, densities are used. This is the power per unit volume, this is the power per unit volume, this is the power per unit area. Fine. Now in actual cases, uh, you know that the nano generators are not for generating very high power. So, in reality, what you see as this power as in general microwatt to, so what you see actually microwatt per uh, centimeter cube, or maybe milliwatt per centimeter cube. This kind of power density are seen in case of piezoelectric material. Okay, now how do you now next, so what you calculate, so the power density which you are getting from here, you just plot it with or initially you just calculate the power uh, what you are getting in the, or power, whatever, I mean power density or power whatever you want to calculate here, and in this you plot the load resistance. So if you plot it like this, so generally, suppose if I take, okay, now let me take this as a power density, so the unit will be, let's say, microwatt per centimeter cube, okay, or square, whatever. So it is power density, you are, that is what you are plotting against the load resistance. So you will see a curve like this, you will see a curve like this. So somewhere you will get the maximum power and then gradually it will fall. Okay, so that will represent the value of the maximum power, that will represent the maximum power at a particular value of the load resistance, at a particular value of the load resistance, which is the optimum RL. This optimum RL you need to find out for your circuit. Okay, now we are talking about the practicality of the circuit which we are dealing with. And so as I told you that in in theoretically you say that VOC is open circuit, so in this case your RL is infinity, right? And short circuit current, how do you measure? Short circuit current you measure when the load resistance is 0. In practical cases, when you measure this load resistance, sorry, this open circuit voltage or short circuit current, so here actually you measure this open circuit voltage at a very fairly high value of the resistance. So you measure this as a fairly at very high resistance, but that is not infinity. Okay, and the short circuit current you measure at a fairly at very low resistance. Sorry, this you measure at a very low, that you measure at a very low resistance. Now here it should be noted that these are only the estimation, right? The VOC values differ slightly from the peak value. Okay, And therefore, if you calculate the output power, okay, if you calculate the output power as, if you calculate the output power P as VOC into short circuit current, uh, this will actually give you an overestimation basically. Okay, this will give you an overestimation. You will get a very high value of power if you calculate the power from directly from VOC and ISC. So this demonstrates that the importance of measuring the power generated across a load rather than using this value. So you should not calculate power from this, but the power from this RL value. Okay. So when so it means that power should always be measured across the load. Okay, to calculate the power density. Okay, so you need to remember that the for practical purpose, the power should always be calculated as a function of RL, and that is, and you will get a maximum power from somewhere else. You will get maximum power for a particular value of RL. That RL should be used to calculate the power. Okay, that should be used to calculate the power. Now, using the power values measured across the load allows significantly more realistic comparison to be made both between different nanostructured energy harvester and between them and the other energy harvester also, because you are comparing their performance. Okay. However, this peak output power is still based on the maximum voltage which is generated in a cycle, because as I told you that if you are calculating the peak value of the power, then it is coming from the peak value of the voltage, and it is an instantaneous power, and it will not, it is giving you the instantaneous power, but this is not the actual power. So power should be measured at a particular value of the RL, and using the rectifier circuit as well as the capacitor circuit and the load resistance that we have seen earlier. Okay, so that is how it should be measured. Okay, now let me take some case studies where how they have measured. So let me just talk about that. Okay, so here is a paper where they have the circuit which I have shown you earlier. Okay, so after I can just take it like this, that after that I can take it like after the rectifier you have a capacitor which is connected here, and after that you sorry after that you are using the load resistance here. Okay, and then this is what is your load resistance. Let me use a different color because it is not very good visible. Okay, and then you are using Here you are actually measuring the V. Okay. And what I said, that VOC is where resistance is very high, and short circuit current is when the resistance is very low. That is the only meaning. Fine. Now, if you plot this voltage which you are measuring here and current, so how do you measure voltage and current? So voltage you can just measure with the DSO, okay, using a DSO, digital storage oscilloscope, okay, using a digital this uh, VOC versus time that can be plotted, and to record the short circuit current versus time, you need to have a nanoammeter. Okay, you have to have a nanoammeter, and there are few more things which is required in doing so. Sometimes they use different nanoammeter, okay, for measuring this thing, and that is done. So for this to measure, you have to have a nano ammeter. Okay, that need to be required. Now, what I was trying to show you, that if you just plot this thing together, here voltage, here the current. So, and this you are varying with load resistance. Okay, so the value, this is a very small current, nano ampere, and this is you will get in volt. So what you will get, this will vary like this, and gradually it will increase. Okay, and the opposite you will see for the current. So current will earlier, when the load resistance value is less, then voltage will be less, and then it will gradually go up, and current will show the different thing. It will be falling like this, or maybe I can use some different colors to represent it. So current will be like this. Current will go and fall down like this. Okay, so you can see that for I think for this particular value of the load resistance, you will get the maximum power. And if you now just plot the power against this, if you plot power against this, so now if you want to plot x-axis load resistance, and this is the power, so this particular value you will get the maximum power. So what you will see, that your it will go, and then there will be a peak value like this. Okay, so this is going to be your maximum power. Sorry, this is going to be your maximum power. Okay, and that you will get for a particular value of the load resistance, that you will get for a particular value of the load resistance. Okay, now For a better performance, average power delivered to that is calculated. And now sometimes the whether it can the whatever the power generated, it can charge a capacitor or not, that is also evaluated. So you use this capacitor here, you use a capacitor here so that you want to see whether it could charge a capacitor or not, and you will try to see that how it is charging and discharging. So you also verify sometimes the charging and discharging behavior of the capacitor. Okay, so you want to see that what is the basically this voltage which you are talking about. This is the voltage which is across the load resistance, and uh, and this also, right? So this is the voltage across the load resistance. Load resistance is the path which is providing complete the circuit, and this has to vary from, as I said, from a very small value to a very higher value.